the Basel series. What's the sum of these terms, you might ask? Well, mathematicians knew it converged, but for centuries they didn't know to what value, until Euler came and proved that it equals pi squared over 6. So let's see how he did it. We'll start by a simple function. Let's say y equals x, and we'll extend it periodically from negative pi to pi. And we can show this algebraically as follows by this equation, and graphically we get a sawtooth function of y equals x that extends periodically as mentioned before. So we'll use these groundwork to get the result that we want. Now we'll make use of the Fourier series expansion of our f of x, which can be presented as a sum from n equals 1 to infinity of the Fourier coefficient bn times sine of nx, and bn, the coefficient, can be represented as 2 over pi times the integral from 0 to pi of x times sine of nx dx. So we get to the calculation of that integral. Utilizing integration by parts, we can let u to be x and dv to be sine of nx dx. If we take a derivative, we get du is equal to dx, and integrating both sides, we get v is negative cosine of nx over n. So we try to put this all together to get the coefficient bn and to get a simple expression as the Taylor series expansion. So we put this together, and since we know that the cosine of n pi is equal to negative 1 to the n plus 1, and sine of n pi is equal to 0, our expression for the coefficient bn and the integral from 0 to pi of x sine of nx dx reduces to pi over n times minus 1 to the n plus 1. Now simplifying, we get bn, the coefficient of the Fourier series, is 2 over n times minus 1 to the power of n plus 1. And what we can do with this coefficient is to put it all together for our expression of the Fourier transform for y, which is equal to 2 times the sum from 1 to infinity of negative 1 to the n plus 1 times sine of nx over n. And we will be using this to get to our final results, which you can see geometrically and how it works as a sawtooth function goes on periodically with respect to our f of x equal to x. Now we get to the fun part. This is where Parsel's identity connects both sides beautifully. So we know by Parsel's identity that the total energy of function equal the sum of the square of its coefficients. So mathematically, for f of x equal to x on negative pi to pi, including negative pi, we can express f of x as the sum of bn times nx, and then squaring both sides, as in Parsel's identity, we get the product of sum over n of bn times sine of nx and sum over m of bm times sine of mx. And if we integrate both sides, we get the expression that you can see. But what we can do with properties of summation and integral is to use the idea of integrating in the summation to get the product of bn and bm times the integral of the product equaling the sum of n and m of bn times bm times pi times the canonical delta, which ultimately all goes down to the integral of negative pi to pi of f of x squared dx is equal to pi times the sum of bn squared over the n. Putting this all together, we get the integral of negative pi to pi of f of x squared, the magnitude dx is integral of negative pi to pi of x squared dx. Using the integration techniques, we get that equals to 2/3 pi cubed, and the sum over the ends of pi times bn squared is nothing but pi times the sum over n of 4 over n squared. So we're getting really close to our desired result of the Basel series. So as you can see geometrically how it behaves, the function x squared, or in this case bn squared, as we sum down those areas under it. So if we put these results algebraically together, we get 4 pi times the sum from 1 to infinity of 1 over n squared is 2/3 pi cubed, and therefore the Basel series sum to pi squared over 6 when we merge the results. Now you might ask how Euler did it. Well, his brilliant idea was to utilize the product function of sine. Well, we can represent sine x as x times the product function from 1 to infinity of 1 minus x squared over n squared times pi squared. And utilizing this product function, we can actually break down the expression into Taylor series components, where sine x is represented as x minus x cubed over 3 factorial, plus the terms that continue within the sine function, the Taylor series expansion, and the product function can be represented as x minus the sum from 1 to infinity of x cubed over n squared times pi squared, plus the terms that continue afterwards. Now, we have to kind of be clever with it because you have to match the coefficients. And if you match the coefficients together, you can see that 1 over 3 factorial, which is the coefficient on the left-hand side, is equal to the sum from 1 to infinity of 1 over n squared times pi squared. So we can see the Basel series in our expression. And if we merge it together, multiplying by pi squared and simplifying the factorial, we get that the sum from 1 to infinity of 1 over n squared is nothing but pi squared over 6. From waves to geometry, from algebra to analysis, the Basel problem is a perfect example of how simple questions can lead to deep and beautiful truths. Thanks for watching, and if you love math and solving problems, subscribe for more. Thank you.